Welcome, friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the strange geometry of space-time itself, where the universe bends and stretches like a cosmic fabric, and time becomes as malleable as clay in the hands of gravity. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Light travels in straight lines through empty space. Yet during a solar eclipse, astronomers observe starlight bending around the sun's edge. This gentle curve reveals Einstein's profound insight. Massive objects warp the very fabric of space-time, creating valleys and hills in what we once imagined as flat, unchanging dimensions. The sun's immense gravity doesn't simply pull on light, it reshapes the geometry through which light must travel, like a bowling ball pressed into a stretched bedsheet. Each photon follows what it perceives as the straightest possible path, unaware that space itself has curved beneath its journey. The measurement of this stellar deflection during the 1919 solar eclipse marked one of science's quietest revolutions. Sir Arthur Eddington's expedition to Principe Island captured photographs showing stars appearing slightly displaced from their expected positions. Their light guided around the sun's gravitational well. The displacement measured just 1.75 arc-seconds, barely the width of a coin viewed from 2 miles away. Yet this infinitesimal shift confirmed that geometry itself could bend under the influence of mass and energy. The expedition team worked through tropical storms and uncertain weather, carrying their delicate photographic plates across thousands of miles to witness light itself following curved paths through space. For centuries before this revelation, scientists had conceived of space and time as separate, absolute entities, an unchanging stage upon which the cosmic drama unfolded. Newton's clockwork universe ticked forward with mechanical precision, its 3 dimensions of space and single dimension of time existing independently, unaffected by the matter and energy they contained. Yet Einstein's equations revealed something far more subtle and profound. Space and time form a unified fabric, flexible and responsive, shaped by every particle of matter and quantum of energy within it. Near the sun's surface, where gravity pulls with tremendous force, time itself moves more slowly than it does here on Earth. A clock placed there would tick measurably behind its earthbound twin, not because of any mechanical failure, but because time dilates in the presence of mass. This isn't science fiction. It's the quiet mathematics of general relativity, confirmed by countless experiments and woven into the GPS satellites that guide our daily journeys. Without accounting for this gravitational time dilation, our navigation systems would drift by several miles each day, accumulating errors that would render them useless within hours. The sun's gravitational field creates what physicists call a metric tensor, a mathematical description of how distances and durations change throughout space-time. This tensor maps the curvature like a topographical chart of an invisible landscape, where steep gradients indicate strong gravitational fields and gentle slopes mark regions of weaker influence. Time flows fastest at the peaks of this gravitational topology and slowest in its deepest valleys. The metric tensor contains 10 independent components, each describing a different aspect of spacetime's curvature. forming a mathematical symphony that orchestrates the dance of planets, the trajectory of light, and the flow of time itself. Mercury, the innermost planet, experiences this temporal stretching most acutely among the solar system's major worlds. Its orbital period, measured by Earth-bound observers, differs subtly from what Mercury's own hypothetical clocks would record. The planet races through spacetime's curved channels, following geodesics, the shortest paths through this warped four-dimensional landscape. Its elliptical orbit slowly precesses, rotating like a cosmic flower blooming over thousands of years, tracing patterns that Newtonian gravity alone cannot explain. This precession amounts to just 43 arcseconds per century. Yet this tiny discrepancy between observation and classical prediction provided one of general relativity's most elegant confirmations. The curvature extends far beyond the Sun's immediate vicinity, creating ripples and flows throughout the solar system's space-time geometry. Each planet contributes its own gravitational signature to this cosmic tapestry, though their effects pale beside the Sun's overwhelming presence. Jupiter, despite its considerable mass, warps spacetime so gently that its time dilation effects remain nearly imperceptible. Yet even these subtle distortions accumulate over astronomical distances, creating a complex landscape of temporal gradients that spacecraft navigation must account for during interplanetary journeys. Scientists still puzzle over whether spacetime is truly curved, or whether gravity represents something else entirely, perhaps the universe's way of preserving some deeper symmetry we haven't yet glimpsed. The equations work perfectly, predicting phenomena with extraordinary precision. Yet the fundamental nature of this curvature remains mysteriously opaque. Some theorists propose that gravity might emerge from quantum entanglement between microscopic degrees of freedom, while others suggest that space-time itself might be discrete rather than continuous at the smallest scales. These questions probe the deepest foundations of physical reality, where geometry, quantum mechanics, and the nature of time itself intersect. The irony rests in how the universe's most massive objects, stars, planets, black holes, become time's gentlest sculptors. They don't break temporal flow but guide it, like rivers carving through stone over geological ages. Only the most extreme gravitational fields reveal time's hidden flexibility, and perhaps most quietly amusing of all, the same force that keeps our feet planted on Earth's surface also grants the universe its capacity for temporal artistry. The coffee cup resting on your table experiences the same fundamental force that could theoretically enable journeys through time itself. Every massive object, from dust grains to galactic clusters, participates in this grand geometric dance, warping space-time according to its energy and momentum. Modern physicists describe this warping like the surface of a trampoline, where heavy objects create depressions that guide the motion of smaller ones. Yet this analogy barely captures the four-dimensional reality, where time and space interweave so completely that separating them becomes meaningless, like trying to distinguish between a wave's height and its forward motion. The actual geometry involves 10 independent components in Einstein's field equations, each describing how matter and energy curve spacetime and how this curvature, in turn, determines the motion of matter and energy. This reciprocal relationship matter tells spacetime how to curve. Spacetime tells matter how to move, forms the conceptual heart of general relativity. Even Earth creates its own modest dimple in spacetime's fabric. Laboratory experiments with atomic clocks have measured the infinitesimal time differences between basement and penthouse levels of skyscrapers. The effect amounts to mere nanoseconds over human lifetimes. yet it demonstrates that temporal flow responds to every gravitational gradient, no matter how gentle. This sensitivity suggests that time travel might not require exotic physics or impossible energies, simply the patient manipulation of matter and space over cosmic scales. The universe, it seems, has woven temporal flexibility into its very foundation. The mathematics reveal something even more profound. Spacetime curvature doesn't just affect how objects move through space and time, it is the motion itself. There is no separate gravitational force pulling objects together. Instead, they follow the straightest possible paths through curved geometry, like marbles rolling along the contours of a warped surface. What we perceive as gravitational attraction emerges naturally from spacetime's intrinsic curvature, making gravity not a force at all, but pure geometry in motion, written in the language of differential equations that describe how the universe bends around every mote of dust and beam of light. Atomic clocks perched atop mountains tick faster than their counterparts nestled in valleys below. This isn't a malfunction of delicate machinery, but a fundamental feature of reality itself. Time flows more swiftly where gravity's grip loosens, more slowly where mass pulls with greater insistence. The National Institute of Standards and Technology maintains cesium atomic clocks so precise they would lose only 1 second over 30 million years. Yet even these extraordinary timepieces reveal temporal gradients across Earth's modest gravitational landscape. The effect manifests measurably between sea level and modest elevations. A clock stationed at the top of Mount Evans in Colorado, rising 14 to 271 feet above sea level, gains approximately 5 microseconds per year compared to its sea level twin. This difference seems negligible until one considers that GPS satellites orbiting 12,500 miles above Earth experience time dilation effects roughly 45 microseconds per day. Without constant correction for these relativistic effects, our navigation systems would accumulate errors of several miles within 24 hours, rendering them essentially useless for precision applications. Each atomic clock measures time by counting the oscillations of cesium atoms as electrons jump between energy levels, precisely 992, 6 to 31, 770 cycles define 1 second. These atomic transitions remain remarkably constant regardless of location. Yet the rate at which they occur relative to distant observers changes subtly with gravitational potential. Near Earth's surface, where space-time curves more sharply, these atomic oscillations appear to slow when observed from higher altitudes. The atoms themselves experience no change from their reference frame. Time passes normally, yet observers at different gravitational potentials measure different durations for identical physical processes. This gravitational time dilation affects more than artificial timepieces. Every biological process, every chemical reaction, every quantum transition occurs at rates determined by local space-time curvature. A hypothetical observer living at sea level would age imperceptibly slower than their mountain-dwelling twin, though the difference would amount to mere nanoseconds over a human lifetime. The effect becomes more pronounced near massive objects. A person standing on the surface of a white dwarf star would experience time passing roughly 1,000 times slower than someone observing from a safe distance. Earth's rotational motion adds another layer of complexity to these temporal variations. The planet's spin creates a subtle frame-dragging effect, where space-time itself rotates slightly around Earth's axis. This Lenz-Thirring effect, predicted by general relativity and confirmed by satellite measurements, means that clocks positioned near Earth's equator experience slightly different temporal flows than those at the poles. the difference amounts to mere picoseconds, yet it demonstrates how motion through space influences the passage of time in ways that would have seemed impossible to pre-relativistic physics. Scientists have verified these predictions through increasingly sophisticated experiments. The Haffel-Keating experiment of 1971 flew cesium atomic clocks around the world on commercial airliners, measuring time differences that matched relativistic predictions within experimental error. More recent experiments have detected gravitational time dilation over vertical distances of less than 3 feet, using optical atomic clocks accurate to 1 part in 10^-19. These measurements probe spacetime structure with unprecedented precision, revealing the geometric foundation underlying temporal flow. The mystery deepens when considering how gravitational time dilation interacts with quantum mechanics. Individual particles experience time according to their local gravitational environment, yet quantum entanglement seems to transcend these temporal gradients. When 2 particles become entangled and one is moved to a different gravitational potential, their quantum correlations persist despite experiencing different rates of temporal flow. This suggests that quantum information might propagate through channels that remain independent of spacetime curvature, hinting at deeper structures underlying physical reality. The irony emerges in how Earth's gentle gravitational field, barely strong enough to curve spacetime noticeably, nonetheless creates measurable temporal landscapes across its surface. Mountain climbers experience time flowing slightly faster than beach walkers, though neither would notice without atomic precision instruments. Perhaps most amusingly, frequent flyers accumulate extra nanoseconds of age compared to ground-bound travelers, making jet lag a genuinely relativistic phenomenon. Even more quietly humorous, the International Space Station's astronauts age slightly slower than Earth's surface dwellers, gaining approximately 0.007 seconds of youth per 6-month mission. The practical implications extend beyond navigation systems into fundamental physics research. Particle accelerators must account for gravitational time dilation when synchronizing equipment at different elevations. Gravitational wave detectors like LIGO require exquisite timing coordination between sites separated by thousands of miles, necessitating precise corrections for local gravitational time dilation effects. These corrections highlight how Einstein's century-old insights continue to shape cutting-edge experimental physics. Deep underground laboratories, where physicists search for dark matter and study neutrino interactions, experience time flowing slightly slower than surface facilities. These subterranean environments, shielded from cosmic radiation and positioned deeper within Earth's gravitational well, create unique temporal conditions that might subtly influence sensitive quantum experiments. The temporal difference amounts to mere nanoseconds, yet it illustrates how gravitational time dilation permeates every aspect of precision science. Climate research has revealed that Earth's gravitational field varies subtly across its surface due to variations in crustal density, underground water distribution, and seasonal ice accumulation. These gravitational anomalies create corresponding variations in local time dilation, though the effects remain far too small to influence biological processes or everyday timekeeping. Nonetheless, they demonstrate that temporal flow responds to every gravitational nuance, from massive geological formations to seasonal changes in ice sheet thickness. The phenomenon suggests that time travel might be occurring continuously around us, though at rates so gentle that we barely notice. Every step up a mountain carries us into a slightly faster flowing temporal stream, while every descent into a valley immerses us in time's slower currents. These gradients create a temporal topography as real as Earth's physical landscape, invisible yet measurable, shaping the fundamental rhythm of existence at every location on our planet's surface. Modern atomic clocks have become so sensitive that they can detect gravitational time dilation over vertical distances comparable to the height of a person. This precision transforms timekeeping from a practical necessity into a tool for probing spacetime's geometric structure, revealing how mass and energy sculpt the temporal dimensions through which all physical processes unfold. A traveller departing Earth at velocities approaching the speed of light returns to find their Earth-bound twin aged decades, while they themselves have experienced only months or years. This twin paradox, once purely theoretical, now finds expression in countless particle accelerator experiments, where muons and other unstable particles live far longer than their stationary counterparts would suggest possible. Time dilation reveals itself not as science fiction, but as the universe's fundamental architecture, where motion through space directly influences passage through time. The mathematics underlying this phenomenon emerge from special relativity's core insight. The speed of light remains constant for all observers, regardless of their relative motion. This seemingly simple principle forces time itself to become elastic, stretching and compressing to preserve light's invariant velocity. As objects approach light speed, their clocks slow dramatically relative to stationary observers. A spacecraft traveling at 90% light speed would experience time passing roughly 2.3 times slower than Earth-based clocks, while at 99% light speed, the factor increases to approximately 7 times slower. Cosmic ray muons demonstrate this principle continuously in Earth's upper atmosphere. These unstable particles, created when high-energy cosmic rays collide with atmospheric nuclei, possess lifetimes of merely 2.2 microseconds when at rest. Yet muons travelling at near-light speeds through the atmosphere survive long enough to reach Earth's surface in detectable numbers. Their extended lifetimes result directly from time dilation from the muon's reference frame. They decay normally, but Earth-based observers measure their lifetimes stretched by factors of 10 or more. The reciprocal nature of time dilation creates apparent paradoxes that resolve only through careful analysis of acceleration phases. During periods of constant relative motion, each observer genuinely measures the other's clocks running slow. There is no absolute reference frame to determine which clock really runs slower. The asymmetry emerges during acceleration phases, when one twin changes reference frames while the other maintains constant motion. These acceleration periods break the symmetry, creating measurable age differences that persist after the travelers reunite. Particle accelerators routinely accelerate electrons, protons, and heavier nuclei to velocities exceeding 99.9% the speed of light. At such speeds, time dilation factors reach thousands or tens of thousands, allowing unstable particles to traverse detector chambers before decaying. The Large Hadron Collider accelerates protons to energies of 6.5 TeV, corresponding to velocities so close to light speed that each proton's gamma factor exceeds 6900. These particles experience time passing nearly 7,000 times slower than stationary observers measure. The energy requirements for achieving significant time dilation effects with macroscopic objects present formidable challenges. Accelerating even a single gram of matter to 90% light speed would require energy equivalent to several hundred nuclear weapons. This energy scales exponentially as velocity approaches the speed of light, making interstellar travel at relativistic speeds an extraordinarily demanding proposition. Yet the universe demonstrates that such energies exist. Cosmic rays occasionally strike Earth's atmosphere with energies exceeding 10 ydin 20 electron volts, corresponding to macroscopic objects traveling at nearly light speed. Scientists have verified time dilation effects using increasingly sophisticated atomic clocks transported on high-speed aircraft and spacecraft. The Global Positioning System provides perhaps the most practical demonstration of relativistic effects, as GPS satellites experience both gravitational time dilation from Earth's weaker gravitational field and kinematic time dilation from their orbital velocities of approximately 14,000 kilometers per hour. The gravitational effect dominates, causing satellite clocks to run fast relative to Earth-based timepieces, while their orbital motion contributes a smaller correction in the opposite direction. The mystery of simultaneity deepens as relative motion increases. Events that appear simultaneous to one observer occur at different times for observers in relative motion. This relativity of simultaneity means that the very concept of now becomes observer-dependent at high velocities. A traveller moving at significant fractions of light speed would disagree with Earth-based observers about the order of distant events, highlighting how motion through space fundamentally alters the structure of spacetime itself. The irony manifests in how faster motion through space results in slower passage through time, as if the universe maintained some cosmic speed limit for motion through spacetime itself. Objects at rest move through time at maximum velocity, while motion through space diverts some of this temporal velocity into spatial dimensions. Perhaps most charmingly, frequent air travellers experience genuine time dilation effects, though the differences amount to mere nanoseconds over a lifetime of flying. Even more subtly amusing orbiting astronauts return to Earth, having aged slightly less than their ground-based contemporaries, making space travel a literal fountain of youth, though the effect remains imperceptible without atomic precision measurements. The biological implications of extreme time dilation remain largely theoretical, yet they raise profound questions about aging, consciousness, and the continuity of experience. Would a traveller experiencing severe time dilation age more slowly at the cellular level? Current understanding suggests that all physical processes, including biological ones, would slow proportionally, making the traveller effectively younger upon return to Earth. This biological time dilation could theoretically allow exploration of the distant future, though the energy requirements remain prohibitive. Modern experiments have pushed time dilation measurements to extraordinary precision using optical atomic clocks. These devices, accurate to 1 part in 1019, can detect time dilation effects from relative velocities as small as a few meters per second. Such precision transforms special relativity from an exotic phenomenon, observable only at extreme velocities, into a measurable effect present in everyday motion. Even walking across a room creates measurable, though infinitesimal, time dilation effects when observed with sufficient precision. The phenomenon extends beyond mechanical timepieces to influence the fundamental constants of physics themselves. High-energy particle interactions occur at rates determined by local time flow, meaning that particles accelerated to near-light speeds experience modified interaction rates from the perspective of laboratory observers. These effects must be carefully accounted for in particle physics experiments, where precise timing measurements are crucial for understanding fundamental interactions. Quantum mechanics adds additional complexity to relativistic time dilation, as quantum processes must remain consistent across different reference frames. The quantum mechanical description of unstable particles includes relativistic corrections that ensure decay rates transform properly under changes of reference frame. This quantum relativistic treatment has enabled precise predictions of particle lifetimes in high-energy experiments, confirming both special relativity and quantum mechanics with extraordinary accuracy. The universe itself provides natural laboratories for extreme time dilation effects. Neutron stars, with surface velocities reaching significant fractions of light speed due to their rapid rotation, experience complex combinations of gravitational and kinematic time dilation. Material orbiting close to black holes can achieve velocities approaching light speed, where time dilation factors become arbitrarily large as objects approach the event horizon. At the event horizon of a black hole, time stretches toward infinity while space curves back upon itself in an endless gravitational embrace. Here, the fabric of spacetime becomes so severely warped that the normal flow of temporal progression grinds to an apparent halt, creating conditions where time travel becomes not merely possible but inevitable. An outside observer watching matter fall toward a black hole would see it slow dramatically as it approaches the event horizon, its clock appearing to tick more and more slowly until it seems frozen at the boundary between known space and the unknowable interior. Stellar mass black holes, formed from the collapse of massive stars, create gravitational fields so intense that they warped spacetime beyond the point of no return. The event horizon marks the boundary where the escape velocity equals the speed of light, not because light lacks sufficient energy to escape, but because spacetime itself curves so sharply that all possible paths lead inexorably inward. This geometric inevitability transforms the event horizon into a one-way membrane through which information and matter can pass inward but never return to the external universe. The Schwarzschild radius defines this critical boundary, calculated as twice the gravitational constant times the object's mass divided by the speed of light squared. For our Sun, this radius would measure approximately 3 kilometers, while Earth's event horizon would span roughly 9 millimeters. These compact dimensions illustrate the extreme compression required to create black holes from ordinary matter. Stellar cores must collapse to densities exceeding nuclear matter by factors of thousands or millions to achieve sufficient gravitational intensity. Near the event horizon, tidal forces stretch in falling matter into elongated shapes that physicists whimsically term spaghettification. The gravitational gradient becomes so steep that an astronaut's feet would experience significantly stronger acceleration than their head, gradually stretching their body along the direction of gravitational pull. For stellar mass black holes, this stretching becomes lethal long before reaching the event horizon, though supermassive black holes with their gentler tidal gradients might allow safe passage across the boundary. The interior of a black hole remains hidden behind the event horizon, accessible to direct observation only through theoretical extrapolation of Einstein's field equations. These calculations suggest that space-time curvature continues increasing toward the center, eventually reaching infinite density and curvature at the singularity. Yet this mathematical infinity likely signals the breakdown of general relativity rather than physical reality, suggesting that quantum gravitational effects become dominant before true singularities form. Time dilation near black holes creates paradoxical scenarios where different observers measure radically different durations for identical events. An astronaut falling into a black hole would experience normal time flow from their perspective, crossing the event horizon in finite proper time and reaching the singularity within seconds or minutes. However, external observers would see this same journey stretched across billions of years, the infalling astronaut appearing to slow dramatically and fade away as their light becomes increasingly redshifted. Hawking radiation provides black holes with a mechanism for gradual evaporation through quantum effects near the event horizon. Virtual particle pairs created by quantum fluctuations occasionally separate at the horizon, with one particle falling inward while its partner escapes as radiation. This process slowly reduces the black hole's mass while increasing its temperature. creating the paradoxical result that smaller black holes radiate more intensely than larger ones. Stellar mass black holes possess temperatures of mere billionths of a Kelvin, making their evaporation timescales incomprehensibly long. The mystery of information preservation deepens around black holes, as quantum mechanics demands that information cannot be truly destroyed, while general relativity suggests that anything crossing the event horizon becomes permanently inaccessible. This information paradox has spawned numerous theoretical proposals, from holographic principles suggesting that all information is encoded on the event horizon's surface, to theories of black hole complementarity, where different observers perceive fundamentally different descriptions of the same events. The irony emerges in how black holes, often portrayed as cosmic destroyers, might actually serve as natural time machines enabling travel to the distant future. An astronaut orbiting close to a black hole's event horizon would experience extreme time dilation, allowing them to witness the evolution of the external universe accelerated to extraordinary rates. Hours spent in the black hole's temporal embrace could correspond to millennia in the outside world. Perhaps most amusingly, black holes transform the ultimate gravitational trap into a potential gateway through time itself. Even more paradoxically, the point of no return becomes a doorway to tomorrow. Rotating black holes, described by the Kerr metric, drag spacetime around their spinning mass through the frame-dragging effect. This rotation creates an ergosphere outside the event horizon, where spacetime itself moves faster than light relative to distant observers. Within the ergosphere, maintaining a stationary position relative to infinity becomes impossible. All matter and energy must rotate in the direction of the black hole's spin. This region enables exotic energy extraction mechanisms like the Penrose process, where objects can gain energy by dropping material into the black hole. The interior geometry of rotating black holes might contain closed time-like curves, theoretical paths through space-time that loop back to their own past. These curves could theoretically enable time travel to earlier epochs, though they remain hidden behind the event horizon and thus inaccessible to external observers. The mathematics of rotating black holes permit such exotic geometries, yet their physical reality remains highly speculative given our limited understanding of quantum gravitational effects. Supermassive black holes, containing millions or billions of solar masses, reside at the centers of most galaxies, including our own Milky Way. These gentle giants create less extreme tidal forces than their stellar mass cousins, potentially allowing matter to cross their event horizons intact. Sagittarius A, the supermassive black hole at our galaxy's center, spans roughly 24 million kilometers in diameter, yet contains over 4 million solar masses within its event horizon. Recent observations of black hole mergers through gravitational wave detection have confirmed many theoretical predictions about these extreme objects. The collision of two black holes creates ripples in spacetime itself that propagate outward at light speed, carrying information about the merger's dynamics. These observations provide our most direct evidence of black holes' existence and behavior, validating Einstein's century-old predictions about gravity's most extreme manifestations. The quantum mechanics of black holes might ultimately resolve the paradoxes surrounding their formation and evaporation. Some theories propose that black holes possess internal structure invisible from outside, with quantum information stored in ways that preserve unitarity while respecting the causal structure of space-time. These ideas push the boundaries of theoretical physics into realms where general relativity and quantum mechanics must be unified. Modern black hole physics explores connections between gravity, thermodynamics, and information theory that suggest deep relationships between spacetime geometry and quantum entanglement. The holographic principle proposes that all information contained within a black hole can be encoded on its two-dimensional event horizon, implying that three-dimensional space might emerge from more fundamental quantum information processing occurring on lower dimensional surfaces. Massive spinning objects twist the very geometry of space around their rotating bulk, creating currents in the cosmic fabric that drag nearby matter and energy along predetermined paths. This frame-dragging effect, predicted by Einstein's field equations and confirmed through precise satellite measurements, reveals how rotation couples with gravity to sculpt space-time in ways that static masses cannot achieve. The universe's largest rotating bodies, from spinning black holes to entire galaxies, become cosmic whirlpools that stir the fundamental medium through which all physical processes unfold. Earth's rotation produces a subtle but measurable frame-dragging effect that influences the orbits of nearby satellites and the behavior of sensitive gyroscopes. The Gravity Probe B mission, launched in 2004, carried 4 ultra-precise gyroscopes into polar orbit to measure this lens-thirring effect with unprecedented accuracy. After accounting for numerous sources of experimental error, the mission confirmed that Earth's spinning mass drags space-time around its rotational axis by approximately 39 milliseconds per year, a deflection smaller than the width of a human hair viewed from 10 miles away. The mathematics of frame dragging emerge from the off-diagonal terms in Einstein's metric tensor, which describe how temporal and spatial coordinates become mixed in the presence of rotating mass. These cross terms encode the geometric relationship between a rotating object's angular momentum and the surrounding spacetime curvature, creating regions where maintaining a fixed orientation relative to distant stars becomes impossible without applying continuous corrective forces. The effect scales with both the object's mass and its rotational velocity, becoming increasingly pronounced near rapidly spinning, massive bodies, neutron stars with their extreme densities and rapid rotation rates, create some of the universe's strongest frame-dragging effects. These stellar remnants, containing more mass than our Sun compressed into spheres merely 20 kilometers across, can rotate hundreds of times per second while maintaining structural integrity through degeneracy pressure. Near a typical neutron star's surface, frame dragging becomes so severe that space-time itself rotates at substantial fractions of the stellar rotation rate, creating a cosmic maelstrom where conventional notions of stationary reference frames break down entirely. The ergosphere surrounding rotating black holes represents frame dragging taken to its logical extreme. Within this region, bounded by the event horizon and an outer surface called the static limit, maintaining a stationary position relative to distant observers becomes physically impossible. All matter and energy within the ergosphere must rotate in the direction of the black hole's spin, regardless of their initial motion or applied forces. This mandatory rotation creates opportunities for energy extraction through processes like the Penrose mechanism, where carefully orchestrated interactions can extract rotational energy from the black hole itself. Pulsar timing provides astronomers with natural laboratories for studying frame-dragging effects around rapidly rotating neutron stars. These cosmic lighthouses emit precisely timed radio pulses that sweep across space like the beam of a rotating searchlight, allowing measurements of orbital dynamics with extraordinary precision. Binary pulsars, where a neutron star orbits another compact object, experience measurable precession effects due to frame dragging that accumulate over years of observation. The PSR J11416545 system demonstrates orbital precession rates that match theoretical predictions for lens-thirring effects around rotating neutron stars. The phenomenon extends beyond individual objects to influence the structure of rotating galaxies and galaxy clusters. Our Milky Way's rotation creates a weak but detectable frame-dragging effect that subtly influences the motion of satellite galaxies and halo stars. Computer simulations suggest that this galactic frame dragging might contribute to the observed alignment of satellite galaxy orbital planes, though distinguishing these effects from other gravitational influences remains challenging given the complexity of galactic dynamics. Scientists have proposed using frame dragging effects for exotic propulsion systems that could theoretically enable faster-than-light travel without violating special relativity. The Alcubierre drive concept exploits the frame-dragging properties of rapidly contracting and expanding spacetime to create a warp bubble that carries a spacecraft along at superluminal velocities. While the energy requirements for such systems remain prohibitively large, they demonstrate how rotating spacetime geometry might someday enable practical time travel and interstellar exploration. The mystery of how frame dragging interacts with quantum mechanics remains largely unexplored, as most observable effects occur in regimes where classical general relativity provides adequate descriptions. Yet near quantum black holes or in the earliest moments after the Big Bang, quantum fluctuations in rotating spacetime might have created complex patterns of frame dragging that influence the formation of cosmic structure. These speculative connections between rotation, quantum mechanics, and cosmology represent frontier areas where theoretical physics pushes beyond well-established experimental confirmation. The irony manifests in how rotation, seemingly a simple mechanical property, fundamentally alters the geometry of space and time around massive objects. A spinning planet or star doesn't merely rotate within pre-existing space-time, but actively reshapes the medium through which it moves, creating feedback loops between matter, motion, and geometry. Perhaps most elegantly, the fastest rotating objects in the universe become the most effective sculptors of spacetime's architecture. Even more subtly, frame dragging means that truly stationary reference frames cannot exist near rotating masses, making rest itself a relative concept dependent on local gravitational dynamics. Modern tests of frame dragging effect require extraordinary experimental precision, as the predicted deflections remain tiny even for Earth mass objects. The Lagios satellites, dense aluminum spheres covered with retroreflectors, serve as passive test masses whose orbital precession can be measured through laser ranging with millimeter accuracy. These measurements, accumulated over decades of observation, have confirmed frame-dragging predictions to within a few percent, providing strong evidence for Einstein's most subtle gravitational predictions. Theoretical investigations of frame dragging reveal connections to fundamental questions about the nature of inertia and the origin of inertial reference frames. Ernst Mach's principle suggests that local inertial properties emerge from the gravitational influence of distant matter, implying that frame-dragging effects might ultimately trace back to the distribution of mass and energy throughout the observable universe. While Einstein hoped that general relativity would fully incorporate Mach's principle, the theory's predictions for frame-dragging represent only a partial realization of these deep connections between local physics and cosmic structure. Laboratory experiments have attempted to detect frame-dragging effects using spinning masses and sensitive gravitational instruments. Though terrestrial objects produce effects far too small for current measurement capabilities, the required sensitivity exceeds current technology by many orders of magnitude, making space-based experiments the only practical approach for testing frame-dragging predictions. Future missions might employ atomic interferometry or laser interferometry to achieve the precision necessary for detecting frame dragging around artificial masses. The phenomenon suggests that rotating massive objects might serve as natural time machines, as regions of severely dragged spacetime could theoretically contain closed time-like curves where travellers could return to their own past. While such exotic geometries remain highly speculative and would likely require conditions far more extreme than any known astrophysical object produces, they demonstrate how rotation adds rich complexity to spacetime's causal structure, opening theoretical pathways through time that static masses cannot provide. Mathematics suggests paths through spacetime that loop back to their own beginning points, creating closed, time-like curves where travellers could theoretically encounter their own past selves. These exotic geometries emerge naturally from Einstein's field equations under certain extreme conditions, though their physical realizability remains one of theoretical physics' most contentious questions. The mathematics permits temporal loops while raising profound questions about causality, free will, and the fundamental structure of physical law. The Gödel solution to Einstein's equations, discovered in 1949 by the renowned logician Kurt Gödel, describes a rotating universe where closed time-like curves exist everywhere throughout space-time. In Gödel's cosmos, sufficiently long journeys through space automatically become journeys through time, allowing travellers to return to any point in their past by following appropriately curved trajectories. This solution demonstrated that general relativity, in principle, permits time travel without requiring exotic matter or impossible energy densities. Cylindrical spacetimes, such as those surrounding infinite rotating cylinders of matter, also generate closed time-like curves through frame-dragging effects. The Tipler cylinder represents perhaps the most studied example, an infinitely long, massive cylinder rotating at nearly light speed drags spacetime around its axis so severely that certain trajectories loop back through time. While infinite cylinders remain unphysical, finite approximations might theoretically produce similar effects, though the engineering challenges would dwarf any conceivable technology. Traversable wormholes, if they could be stabilized with exotic matter possessing negative energy density, might naturally evolve into time machines through differential aging effects. A wormhole connecting two regions of space could be converted into a temporal gateway by accelerating one mouth to high velocity while keeping the other stationary. The accelerated mouth would age more slowly due to time dilation, creating a temporal offset between the wormhole entrances. Travellers entering the younger mouth could emerge from the older mouth in their own past. Van Stockham's spacetime, describing the geometry around an infinite rotating dust cylinder, contains regions where closed time-like curves become possible for observers following certain trajectories. These solutions demonstrate that rotation alone, without requiring exotic matter, can create the geometric conditions necessary for temporal loops. The effect arises from frame dragging, becoming so severe that spacetime itself rotates faster than light relative to distant observers, enabling trajectories that curve back through time. The Alcubierre warp drive, originally conceived as a faster-than-light propulsion system, can be modified to create closed time-like curves by arranging multiple warp bubbles in carefully choreographed patterns. These configurations would theoretically allow spacecraft to arrive at their destinations before departing, creating temporal paradoxes identical to those associated with conventional time travel. The energy requirements remain astronomical, involving negative energy densities far beyond current technological capabilities. Cosmic strings, hypothetical one-dimensional defects in spacetime that might have formed during the universe's earliest moments, could theoretically enable time travel through their distinctive gravitational properties. Two cosmic strings moving past each other at relativistic velocities create frame-dragging effects that might generate closed time-like curves in their wake, While cosmic strings remain purely hypothetical, their potential existence illustrates how topological defects in spacetime could serve as natural time machines. Quantum mechanics adds additional complexity to closed time-like curves through the potential for quantum interference effects along temporal loops. The Novikov self-consistency principle suggests that quantum mechanics might enforce consistency in the presence of closed time-like curves, allowing only those events to occur that remain logically consistent with the timeline's causal structure. This principle would prevent classical paradoxes like the grandfather paradox, while permitting quantum superpositions of multiple consistent histories. The mystery of how physical laws would behave in the presence of closed time-like curves remains largely unresolved. As most proposed solutions exist in regimes where quantum gravitational effects become important, classical general relativity provides the geometric framework for temporal loops. Yet quantum field theory in curved spacetime suggests that vacuum fluctuations might destabilize closed time-like curves before they could form. This quantum censorship mechanism might represent nature's way of protecting causality from temporal paradoxes. The irony emerges in how the universe's most fundamental theory of space and time permits violations of our most basic assumptions about temporal ordering and causality. Einstein himself expressed discomfort with closed, time-like curves, yet they arise naturally from his field equations under a variety of physically plausible conditions. Perhaps most paradoxically, the mathematics that describes the smooth flow of time also permits its reversal and looping. Even more amusingly, some solutions allow travelers to become their own ancestors, making genealogy a relativistic field requiring careful attention to temporal topology. Recent research into the information-theoretic aspects of closed time-like curves suggests that quantum information theory might provide new insights into their physical realizability. Quantum computation with closed time-like curves would theoretically allow certain problems to be solved instantaneously, as information could be sent back in time to provide its own solution. These studies probe the fundamental relationships between information, computation, and the causal structure of spacetime itself. The AD-CFT correspondence, a powerful tool in theoretical physics that relates gravity theories to quantum field theories, provides new perspectives on closed time-like curves through the holographic principle. In some holographic models, closed time-like curves in the gravitational theory correspond to perfectly causal processes in the dual quantum theory, suggesting that temporal paradoxes might be artifacts of our limited perspective rather than fundamental physical impossibilities. Experimental searches for cosmic strings and other exotic spacetime geometries continue through gravitational wave astronomy and precision tests of general relativity. The LIGO and Virgo detectors could potentially observe gravitational waves generated by cosmic string oscillations or other topological defects, providing indirect evidence for the exotic spacetime geometries that enable closed time-like curves. While no such signals have been detected, ongoing improvements in sensitivity continue expanding our ability to probe spacetime's most exotic possibilities. The phenomenon connects to fundamental questions about the nature of time itself, and whether temporal flow represents an objective feature of reality, or merely a consequence of our limited perspective. If closed time-like curves exist, they might reveal that time's apparent unidirectional flow emerges from statistical or thermodynamic considerations rather than fundamental physical law. This perspective would transform time travel from a violation of natural law into a natural consequence of spacetime's geometric structure. Modern approaches to quantum gravity, including string theory and loop quantum gravity, attempt to resolve the paradoxes associated with closed time-like curves through fundamental modifications, to spacetime's structure at microscopic scales. These theories suggest that spacetime itself might be quantized or emergent, with temporal loops forbidden by the discrete nature of space and time at the Planck scale. Such resolution would preserve causality while explaining why classical general relativity permits seemingly impossible geometric configurations. The study of closed time-like curves has profoundly influenced our understanding of physical laws, relationship to logic and mathematics. These investigations probe the boundaries between mathematical possibility and physical reality, exploring how abstract geometric concepts translate into observable phenomena. Whether or not time travel proves possible, the mathematical exploration of temporal loops has enriched our understanding of spacetime's fundamental structure and the deep connections between geometry, causality, and information. Theoretical tunnels through space could connect distant regions of the universe, folding the cosmic fabric like origami to create shortcuts across otherwise impossible distances. These wormholes, formerly known as Einstein-Rosen bridges, emerge naturally from the mathematics of general relativity as solutions describing spacetime geometries that curve back upon themselves. While their existence remains purely theoretical, wormholes represent perhaps the most elegant pathway to practical time travel, transforming the universe's vast scales from barriers into gateways. The simplest wormhole solutions describe non-traversable passages that collapse faster than light could cross them, making them useless for transportation despite their exotic geometric properties. The original Schwarzschild wormhole connects two black hole event horizons through a narrow throat that pinches closed before any signal could traverse its length. These mathematical constructs demonstrated that space-time topology could be far richer than intuition suggests. Even when physical passage remains impossible, traversable wormholes require exotic matter with negative energy density to maintain their stability against gravitational collapse. This hypothetical material would possess negative mass, creating repulsive gravitational effects that counteract the normal tendency for massive objects to attract. The amount of exotic matter needed scales with the wormhole's throat radius larger. More practical wormholes demand correspondingly vast quantities of negative energy matter, distributed throughout their structure. The Casimir effect provides physics' only confirmed example of negative energy density, arising from quantum vacuum fluctuations between closely spaced conducting plates. These fluctuations create measurable attractive forces that correspond to negative energy densities in the region between the plates. However, the total negative energy remains infinitesimal compared to what traversable wormholes would require, and extracting this energy for macroscopic applications appears impossible with any conceivable technology. Morris-Thorne wormholes represent the most thoroughly studied class of traversable geometries, designed specifically to permit safe passage for human travelers. These solutions avoid horizons, singularities, and extreme tidal forces that would destroy conventional matter, creating smooth space-time geometries that connect distant regions through relatively benign passages. The throat geometry resembles a three-dimensional version of a mathematical saddle, curving outward in some directions while maintaining connectivity between the two asymptotic regions. Converting a traversable wormhole into a time machine requires creating a temporal offset between its two mouths through differential aging effects. One mouth could be accelerated to high velocity while the other remains stationary, causing time dilation to create an age difference between the wormhole entrances. Alternatively, one mouth could be moved into a strong gravitational field where time passes more slowly, achieving similar temporal displacement through gravitational time dilation rather than kinematic effects. The Roman configuration describes a specific time machine scenario where one wormhole mouth orbits a massive object while the other remains in flat spacetime. As the orbiting mouth experiences time dilation from both its orbital velocity and the gravitational field, it ages more slowly than its stationary partner. Eventually, the age difference becomes large enough that travellers entering the younger mouth emerge from the older mouth in their own past, creating a functional time machine. Quantum effects near wormhole throats might destabilize these exotic geometries through vacuum polarization and other field-theoretic processes. The Hawking radiation analog for wormholes suggests that quantum fluctuations could create runaway feedback loops that either collapse the wormhole or expand it uncontrollably. These quantum instabilities represent one of the primary obstacles to wormhole formation, as maintaining the precise balance of exotic matter required for stability becomes increasingly difficult in the presence of quantum corrections. The mystery of wormhole interiors deepens when considering how different physical laws might apply within these exotic geometries. The interior regions of wormholes could theoretically support different vacuum states, alternative particle physics, or modified gravitational interactions that remain invisible to external observers. These possibilities raise fundamental questions about the universality of physical law and whether space-time topology could influence the behavior of matter and energy in unprecedented ways. The irony manifests in how wormholes could theoretically make the universe's most distant regions more accessible than nearby locations, depending on the distribution of wormhole mouths throughout space. A sufficiently dense network of traversable wormholes would transform cosmic geography entirely, making travel time independent of spatial separation in any conventional sense. Perhaps most paradoxically, the shortest path between 2 points might lead through regions of space billions of light-years away. Even more amusingly, wormhole-enabled time travel could make yesterday more accessible than tomorrow, turning temporal navigation into a geometric rather than chronological problem. Microscopic wormholes might form spontaneously through quantum fluctuations at the Planck scale, creating a dynamic foam of tiny space-time tunnels that constantly appear and disappear. These quantum wormholes would exist for infinitesimal durations and span distances smaller than atomic nuclei, yet they might influence the vacuum structure of space-time in measurable ways. Some theories propose that virtual particles could traverse these microscopic passages, creating non-local correlations that might explain certain quantum mechanical phenomena. The holographic principle suggests deep connections between wormhole geometry and quantum entanglement, implying that traversable wormholes might emerge from strongly entangled quantum systems. In this view, wormholes represent the geometric manifestation of quantum information processing, with the wormhole throat corresponding to the entanglement entropy between different regions of space. These ideas blur the distinction between geometry and information, suggesting that space-time itself might be an emergent property of more fundamental quantum correlations. Laboratory analogies to wormhole physics have been created using metamaterials and carefully designed optical systems that mimic the propagation of electromagnetic waves through exotic space-time geometries. While these systems cannot create actual gravitational wormholes, they demonstrate how wave propagation can be controlled to simulate the effects of non-trivial space-time topology. These analog systems provide testing grounds for wormhole theories and might reveal new insights into the behavior of fields in curved space-time. String theory provides theoretical frameworks for wormhole formation through brane dynamics and higher dimensional geometry. In these models, our familiar three-dimensional space might be embedded within higher dimensional spaces where wormhole formation becomes more natural. The extra dimensions could provide the geometric flexibility necessary for creating stable wormholes without requiring exotic matter, though these configurations would exist primarily in the higher dimensional space rather than our observable universe. Modern cosmological models incorporate wormhole-like structures in theories of eternal inflation and the multiverse, where different bubble universes might connect through wormhole passages. These cosmic-scale wormholes could theoretically enable travel between different regions of the multiverse, each with potentially different physical laws and constants. Such structures would represent the ultimate expression of wormhole physics, connecting not just distant locations but entirely separate cosmic realms. The search for observational signatures of wormholes continues through gravitational wave astronomy and precision tests of gravitational theory. Wormholes would create distinctive gravitational lensing effects and could potentially generate characteristic gravitational wave signals if they undergo oscillations or mergers. While no such signatures have been detected, ongoing improvements in observational capabilities continue expanding our ability to probe spacetime's most exotic theoretical possibilities. One-dimensional flaws in reality's structure might accelerate time travel through their gravitational wake, creating cosmic highways where space and time bend around defects thinner than atomic nuclei yet stretching across galactic distances. These cosmic strings, hypothetical remnants from the universe's earliest moments, represent topological scars left over from phase transitions during cosmic inflation. Their exotic gravitational properties could theoretically enable time travel without requiring the exotic matter needed for traversable wormholes. Cosmic strings would possess extraordinary linear mass densities while maintaining negligible thickness, creating gravitational fields unlike any produced by conventional matter. A cosmic string with the mass of Earth's Sun spread across a single light year would weigh approximately 10-13 kilograms per meter, roughly equivalent to a mountain compressed into a line thinner than a proton. These extreme densities arise from the string's topological nature as one-dimensional defects in the fabric of spacetime itself. The gravitational field around a static cosmic string produces no acceleration toward the string's center, unlike conventional massive objects that attract nearby matter through spherically symmetric gravitational wells. Instead, cosmic strings create conical spacetime geometry where parallel light rays remain parallel after passing the string. Though they converge when viewed from certain angles, this unusual gravitational behavior results from the string's infinite length and perfectly uniform linear mass distribution. Moving cosmic strings generate gravitational waves that propagate outward from the string's trajectory, carrying away energy and angular momentum while creating distinctive signatures detectable by gravitational wave observatories. Two cosmic strings passing each other at relativistic velocities would produce characteristic burst patterns in detectors like LIGO and Virgo, offering potential observational evidence for these exotic objects. The gravitational wave signals would possess unique features distinguishing them from black hole mergers or neutron star collisions. Frame-dragging effects around moving cosmic strings become particularly pronounced when strings move at velocities approaching the speed of light. The space-time geometry behind such strings differs measurably from the geometry ahead of them, creating asymmetric gravitational fields that could theoretically enable time travel. An observer following a carefully planned trajectory around two cosmic strings moving past each other might return to their starting point, having travelled backward through time. The GOT time machine exploits frame dragging around cosmic string pairs to create closed time-like curves without requiring exotic matter energy conditions beyond the strings themselves. Two infinite cosmic strings moving past each other at appropriate velocities and trajectories create regions of space-time where causal loops become possible through purely geometric effects. The required string velocities must exceed roughly half the speed of light, making this scenario depend on cosmic strings achieving extreme relativistic motion through some astrophysical mechanism. Oscillating cosmic strings would create time-dependent gravitational fields that periodically compress and expand the surrounding spacetime, potentially generating regions where temporal flow becomes temporarily reversed. These oscillations could arise from the string's internal dynamics or interactions with other cosmic structures, creating complex patterns of gravitational radiation that propagate outward at light speed. The resulting spacetime distortions might create brief windows of opportunity for time travel near the oscillating string segments. Cosmic string networks, if they exist, would create complex patterns of gravitational interaction that could amplify the time travel effects of individual strings. Multiple strings intersecting at various angles would generate intricate space-time geometries where closed time-like curves might form more readily than around isolated strings. The network's evolution over cosmic time would create a dynamic landscape of temporal possibilities, with new time travel opportunities appearing and disappearing as the string configuration changes. The mystery surrounding cosmic string formation connects to fundamental questions about the universe's earliest moments and the nature of symmetry breaking during cosmic phase transitions. These strings would represent fossilized evidence of physical processes occurring when the universe was less than 10 or 35 seconds old, potentially preserving information about energy scales far beyond current experimental accessibility. Their detection would provide unprecedented insights into physics at the grand unification scale. The irony emerges in how these hypothetical cosmic flaws could serve as the universe's most efficient time machines, requiring no exotic matter or impossible energy sources beyond their own existence. The very imperfections that cosmic strings represent topological defects in space-time structure become pathways for transcending normal temporal limitations. Perhaps most elegantly, the universe's scars from its violent birth could enable exploration of its own past. Even more paradoxically, cosmic strings demonstrate how linear objects could facilitate non-linear temporal trajectories, transforming one-dimensional defects into gateways through the fourth dimension. Superconducting cosmic strings, if they exist, would carry persistent electrical currents along their length, creating magnetic fields that interact with charged particles throughout the cosmos. These electromagnetic effects would add additional complexity to the string's gravitational influence, potentially creating hybrid gravitational electromagnetic time machines that operate through combinations of curved spacetime and electromagnetic field dynamics. The resulting physics would blend general relativity with electrodynamics in novel ways. Numerical simulations of cosmic string evolution reveal complex dynamics as strings stretch, oscillate, reconnect, and fragment under their own gravitational stresses. These simulations suggest that cosmic string networks would evolve toward configurations that minimize their total energy, potentially creating preferred geometries for time travel applications. The network's self-organization might naturally produce the string arrangements most conducive to closed time-like curve formation. Observational constraints on cosmic strings come primarily from gravitational wave searches and cosmic microwave background observations, both of which place upper limits on the possible abundance and properties of cosmic string networks. Current data suggests that if cosmic strings exist, their linear mass density must be relatively small compared to early theoretical predictions. These constraints limit the time travel potential of cosmic strings, though they don't completely rule out their existence or their exotic gravitational properties. The cosmic string tension, the energy per unit length stored in the string's internal structure, determines the strength of gravitational effects around the string, and thus the feasibility of time travel applications. Higher tension strings create stronger gravitational fields and more pronounced frame dragging effects, making time travel more accessible, but also increasing the energy requirements for string formation and stability. The tension depends on the specific symmetry breaking scenario that created the strings during the early universe. Alternative models of cosmic strings include fundamental strings from string theory, which would possess different physical properties than topological cosmic strings arising from field theory phase transitions. Fundamental strings could theoretically achieve much higher tensions and create stronger gravitational effects, though their quantum nature might introduce stabilization mechanisms that prevent the formation of closed time-like curves. These distinctions highlight how different approaches to fundamental physics predict different possibilities for cosmic string time machines. Modern theoretical work on cosmic strings explores their role in cosmological models featuring extra dimensions, where strings might represent higher dimensional objects intersecting our three-dimensional space. These brane-world scenarios could provide mechanisms for cosmic string formation that bypass some of the constraints imposed by four-dimensional field theory, potentially enabling more exotic string configurations with enhanced time travel capabilities. The detection of cosmic strings would revolutionize both cosmology and fundamental physics, providing direct evidence for physics beyond the standard model and potentially opening new avenues for understanding spacetime's deepest structure. Whether or not they enable time travel, cosmic strings represent one of theoretical physics' most elegant predictions, simple topological defects that could preserve information from the universe's first moments while creating the most exotic gravitational phenomena imaginable. Physics equations work backward and forward equally, yet entropy flows in one direction only, creating the profound mystery of time's arrow that distinguishes past from future in our everyday experience. The fundamental laws governing particles, fields, and forces remain unchanged when time runs in reverse, suggesting that the universe's microscopic constituents know nothing of temporal direction. Yet everywhere we observe irreversible processes: eggs breaking, stars burning, memories forming that define a clear temporal arrow pointing from ordered past toward disordered future. Thermodynamics provides the clearest expression of temporal asymmetry through its second law, which states that entropy, a measure of disorder or information content, tends to increase in isolated systems. This statistical tendency emerges from the overwhelming numerical advantage of disordered states over ordered ones, making the spontaneous decrease of entropy extraordinarily unlikely, though not strictly impossible. A broken egg could theoretically reassemble itself, but the probability remains so vanishingly small that such events never occur in practice. Maxwell's demon, a thought experiment proposed by James Clerk Maxwell, highlights the connection between information and entropy by imagining a microscopic being capable of sorting fast and slow molecules between two chambers. This demon could theoretically decrease a system's entropy by creating temperature differences without performing work, apparently violating the second law of thermodynamics. Resolution of this paradox requires accounting for the entropy increase associated with the demon's memory and information processing capabilities. Boltzmann's H-theorem provides a mathematical framework for understanding entropy increase in terms of molecular collisions and statistical mechanics. The theorem demonstrates that molecular chaos, the assumption that particle velocities remain uncorrelated between collisions, inevitably leads to entropy increase over time. Yet the underlying equations of molecular motion remain time-reversible, suggesting that time's arrow emerges from statistical assumptions rather than fundamental physical law. Cosmological models suggest that the universe began in an extraordinarily low entropy state following the Big Bang, providing an initial condition that enables entropy increase over cosmic timescales. This cosmological arrow of time aligns with the thermodynamic arrow through the universe's expansion and cooling, which allows increasingly complex structures to form while overall entropy continues rising. The mystery deepens when considering why the universe possessed such special initial conditions that enabled billions of years of entropy increase. Quantum mechanics introduces additional complexity through the measurement problem, where quantum superpositions collapse into definite states during observation. This collapse process appears irreversible and provides another potential source for time's arrow, though the fundamental Schrödinger equation remains time-symmetric. Some interpretations of quantum mechanics, such as the many-worlds interpretation, eliminate collapse entirely and restore microscopic time reversibility at the cost of multiplying universes. Black hole thermodynamics reveals deep connections between gravity, entropy, and information that challenge our understanding of temporal irreversibility. The Bekenstein-Hawking entropy formula relates a black hole's entropy to its surface area rather than its volume, suggesting that information might be encoded holographically on event horizon boundaries. The subsequent evaporation of black holes through Hawking radiation creates the information paradox whether quantum information falling into black holes is permanently lost or somehow preserved. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, contains no explicit time parameter and thus appears to eliminate temporal flow entirely at the most fundamental level. This timeless perspective suggests that the experience of temporal passage might emerge from the universe's internal correlations and the way information becomes organized within quantum gravitational systems. Time's arrow could represent a macroscopic approximation rather than a fundamental feature of reality. Causal set theory proposes that spacetime itself consists of discrete events ordered by causal relationships, potentially providing a microscopic foundation for temporal direction. In this framework, time's arrow emerges from the partial ordering of causally connected events, making temporal direction an intrinsic feature of spacetime's atomic structure. The theory suggests that temporal flow arises from the universe's causal network rather than from thermodynamic or quantum mechanical considerations. The mystery of temporal direction deepens when considering how different physical processes seem to define conflicting arrows of time. The thermodynamic arrow points toward increasing entropy. The cosmological arrow follows universal expansion. The electromagnetic arrow follows retarded radiation solutions, and the quantum mechanical arrow might follow state vector reduction. The remarkable fact that these arrows align in our observable universe suggests deep connections between seemingly unrelated physical phenomena. The irony manifests in how the universe's most fundamental equations ignore temporal direction, while our most direct experiences depend entirely upon time's irreversible flow. Every memory, every aging process, every cause and effect sequence presupposes temporal asymmetry that finds no reflection in basic physical law, perhaps most paradoxically. The equations that perfectly describe time's passage contain no inherent concept of temporal direction. Even more mysteriously, time travel into the past would seem to require reversing entropy flows that statistical mechanics deems virtually impossible, making temporal paradoxes thermodynamically unlikely, regardless of spacetime geometry. Fluctuation theorems in modern statistical mechanics describe rare events where entropy temporarily decreases, providing glimpses of time-reverse behavior in small systems over short durations. These fluctuations become increasingly probable as system size decreases and observation time shortens, suggesting that microscopic time reversal occurs continuously around us. Advanced experimental techniques have observed individual molecular motors running backward and heat flowing from cold to hot reservoirs, demonstrating that time's arrow becomes increasingly flexible at microscopic scales. The emergence of complexity and life represents another temporal arrow that seems to run counter to thermodynamic expectations. While overall entropy increases, local regions can become increasingly organized through energy flows that create complex structures far from thermal equilibrium. This complexity arrow might provide clues about how ordered patterns emerge and persist, despite the general tendency toward disorder, potentially revealing new principles governing temporal direction in open systems. Retrocausality in quantum mechanics suggests that some quantum processes might be influenced by future measurements, creating subtle backward-in-time correlations that preserve overall statistical patterns while allowing limited information flow from future to past. These effects remain highly speculative and would operate within the constraints of thermodynamic and causal limitations, but they hint at how quantum mechanics might naturally incorporate temporal flexibility without violating macroscopic causality. Modern approaches to quantum gravity attempt to understand how temporal direction emerges from more fundamental timeless laws through mechanisms like spontaneous symmetry breaking or the holographic principle. These theories suggest that time's arrow might result from the way information becomes organized in quantum gravitational systems, making temporal direction an emergent property rather than a fundamental input to physical law. The arrow of time problem illustrates the deep mystery surrounding our most basic temporal intuitions and their relationship to fundamental physics. Whether time travel proves possible or impossible, understanding why time flows in one direction remains one of physics' most profound challenges, connecting thermodynamics, quantum mechanics, cosmology, and the nature of consciousness in ways that continue to surprise and puzzle theoretical physicists. Subatomic particles seem to influence their own past states through quantum entanglement effects that transcend classical notions of temporal ordering and causality. These quantum correlations persist across space-like separations where no causal influence should be possible according to special relativity. Yet experimental tests consistently confirm non-local correlations that appear to operate outside conventional spacetime constraints. The phenomenon suggests that quantum mechanics might naturally incorporate backward-in-time influences that remain invisible at macroscopic scales. The Einstein-Podolsky-Rosen paradox highlighted quantum mechanics' non-local character by describing entangled particles that maintain correlated properties regardless of spatial separation, when measurement of one particle instantly determines the properties of its distant partner. The correlation seems to require faster-than-light communication, or some form of backward causation that establishes the correlation before measurement occurs. Bell's theorem proved that no local hidden variable theory could account for these correlations, forcing physicists to accept either non-locality or retrocausality as fundamental features of quantum reality. Delayed choice experiments demonstrate quantum mechanics' temporally counterintuitive character by showing how future measurements can retroactively determine past quantum states. In these experiments, the decision to measure wave or particle properties occurs after photons have already passed through experimental apparatus. Yet the measurement choice determines whether the photons behaved as waves or particles during their earlier passage. This temporal flexibility suggests that quantum systems exist in superposition states that remain undetermined until measurement collapses them into definite configurations. The quantum eraser experiment extends delayed choice concepts by showing how information about quantum paths can be acquired and subsequently erased, with the erasure retroactively affecting interference patterns that formed before the erasure occurred. When path information becomes available, interference disappears. When the information is erased, interference returns, regardless of the temporal ordering of these operations. These results challenge conventional notions of temporal causality and suggest that quantum information might flow backward through time under certain circumstances. Wheeler's participatory universe concept proposes that conscious observation plays a fundamental role in determining quantum reality through a self-consistent loop where the universe's present state influences its past through quantum measurements. In this view, the act of observation helps create the very reality being observed, establishing a temporal feedback loop that connects present measurements with past quantum states. This interpretation suggests that consciousness might be fundamentally intertwined with quantum mechanics' temporal properties. Quantum tunneling exhibits temporal characteristics that seem to violate classical causality by allowing particles to traverse barriers faster than light could cross the same distance. Measurements of tunneling times have yielded controversial results, suggesting zero or even negative transit times, implying that particles emerge from barriers before they enter them. While these interpretations remain highly debated, they illustrate how quantum mechanics challenges conventional notions of temporal ordering at microscopic scales. The transactional interpretation of quantum mechanics, developed by John Cramer, explicitly incorporates retrocausality by describing quantum interactions as transactions between advanced and retarded waves, propagating forward and backward through time. In this formalism, quantum events result from negotiations between future and past states that establish self-consistent solutions to the wave equation. This approach naturally explains quantum non-locality, while introducing explicit backward-in-time influences at the quantum level. Weak measurement techniques allow gentle probing of quantum systems without completely collapsing their wave functions, revealing strange temporal correlations where measurement outcomes seem influenced by future measurements of related systems. These correlations persist even when the measurements are space-like separated, suggesting that quantum information might propagate through temporal channels that bypass spatial limitations. The effects remain subtle and require sophisticated statistical analysis to detect, yet they consistently reveal non-classical temporal correlations. Quantum error correction demonstrates how quantum information can be preserved against decoherence through encoding schemes that distribute information across multiple quantum systems. Some theoretical proposals suggest that quantum error correction might naturally incorporate temporal encoding, where information becomes distributed across past and future quantum states. This temporal error correction could theoretically enable quantum information to influence its own past states through self-referential feedback loops. The mystery of quantum measurement reveals how the transition from quantum superposition to classical definiteness might involve temporal non-locality that connects measurement outcomes with pre-measurement quantum states. The measurement problem asks why definite outcomes emerge from indefinite quantum superpositions, and some proposed solutions involve retrocausal influences that ensure consistency between quantum predictions and measurement results. These approaches suggest that classical reality might emerge through temporal negotiations between quantum possibilities. The irony manifests in how quantum mechanics, the theory describing nature's smallest scales, might provide the most natural framework for understanding time travel and temporal paradoxes. While macroscopic objects seem bound by classical causality, quantum particles routinely exhibit temporal flexibility that would seem impossible for larger systems. Perhaps most paradoxically, the quantum realm that underlies all physical reality operates according to temporal principles that contradict our everyday experience of causal ordering. Even more mysteriously, quantum entanglement suggests that spatially separated events might be temporally connected in ways that transcend both space and time as classically conceived. Quantum field theory in curved spacetime reveals additional temporal complexities where virtual particles near event horizons exhibit correlations that span past and future light cones. The Unruh effect and Hawking radiation both arise from quantum field fluctuations that connect different regions of spacetime through particle creation processes. These phenomena suggest that quantum mechanics and general relativity together create natural mechanisms for information exchange across temporal boundaries that would be forbidden in purely classical theories. Recent experiments with quantum computers have explored the possibility of implementing quantum algorithms that utilize closed time-like curves, allowing quantum information to influence its own initial conditions through temporal loops. These theoretical quantum time machines would operate through self-consistent feedback where computational outcomes determine their own inputs, potentially enabling the solution of classically intractable problems through temporal bootstrap mechanisms. While purely theoretical, these studies reveal deep connections between quantum information processing and temporal structure. The quantum Zeno effect demonstrates how frequent measurements can freeze quantum evolution, effectively stopping time for quantum systems through repeated observation. Conversely, the anti-Zeno effect shows how appropriately timed measurements can accelerate quantum processes, suggesting that measurement timing provides a mechanism for controlling temporal flow at quantum scales. These effects illustrate how consciousness and measurement might naturally couple to quantum systems' temporal properties. Entanglement swapping experiments create quantum correlations between particles that have never directly interacted, establishing non-local connections through intermediate entangled pairs. The temporal ordering of these operations can be arranged so that entanglement is established before the particles exist in their entangled states, creating apparent retrocausal influences that propagate backward through quantum correlation networks. These experiments push the boundaries of quantum non-locality into explicitly temporal domains. Modern interpretations of quantum mechanics continue grappling with its temporal implications, from many worlds theories that eliminate temporal asymmetry by allowing all possible histories to coexist, to pilot wave theories that restore determinism through hidden variables that might propagate backward in time. These diverse approaches highlight how quantum mechanics' relationship with time remains one of physics' deepest mysteries, connecting fundamental questions about reality, consciousness, and the nature of temporal flow. Hypothetical particles moving backward through time challenge causality's fundamental assumptions by traveling faster than light and arriving at their destinations before they depart. These tachyons, named from the Greek word for swift, exist only in theoretical physics as solutions to relativistic equations that describe particles with imaginary mass and superluminal velocities. Their mathematical existence raises profound questions about the nature of causality, the structure of space-time, and whether faster-than-light communication might be possible without violating physical law. Special relativity's energy-momentum relation permits solutions corresponding to particles with imaginary rest mass. Though such particles would possess real energy and momentum when traveling faster than light, tachyons would experience reverse time dilation compared to ordinary matter. They would slow down when gaining energy and accelerate when losing energy. creating counterintuitive dynamics that violate everyday intuitions about motion and causality. Their existence would require a complete revision of our understanding of particle physics and temporal ordering. The tachyon field appears naturally in certain spontaneous symmetry-breaking scenarios where scalar fields develop negative mass-squared terms in their potential energy functions. These fields would be unstable in their symmetric state and would rapidly evolve toward configurations that minimize their energy, potentially creating observable signatures in cosmological evolution or particle physics experiments. However, the final state of tachyonic field evolution typically involves the field settling into a stable configuration with positive mass-squared terms. Quantum field theory with tachyons leads to complex mathematical structures where the vacuum state becomes unstable and spontaneous. Particle creation occurs continuously. These instabilities suggest that tachyon fields cannot exist in isolation, but must be embedded within larger theoretical frameworks that stabilize their dynamics through interactions with other fields. String theory incorporates tachyonic modes in certain compactification schemes. Though these modes typically signal the need for theoretical modifications rather than representing physically observable particles, faster-than-light signaling using tachyons would enable violations of causality through the construction of causal loops where information influences its own past states. Two observers in relative motion could theoretically exchange tachyonic signals that arrive before they are sent from each observer's perspective, creating closed causal chains that permit communication with the past. This possibility led many physicists to conclude that tachyons cannot exist as stable particles in any physically realistic theory. The reinterpretation principle, proposed to resolve tachyonic causality paradoxes, suggests that tachyons traveling backward in time should be interpreted as antimatter, tachyons traveling forward in time. This reinterpretation preserves causality by eliminating faster-than-light information transfer while maintaining the mathematical consistency of tachyonic solutions. Under this interpretation, apparent backward time travel becomes forward time travel by antiparticles, restoring conventional causal ordering. T-ionic condensation in field theory describes phase transitions where T-ionic field modes become massive through spontaneous symmetry, breaking, transforming unstable vacuum states into stable configurations. This process occurs in various theoretical contexts, from the Higgs mechanism in electroweak theory to brane dynamics in string theory. The condensation typically eliminates tachyonic instabilities by generating effective masses that convert superluminal modes into conventional massive particles. Extended supergravity theories contain tachyonic modes in their spectrum under certain conditions, particularly when compactified from higher dimensional spacetimes. These modes often signal inconsistencies in the compactification scheme or the need for additional stabilization mechanisms. The presence of tachyons in supergravity typically indicates that the theory requires modification to achieve phenomenological viability, rather than predicting observable faster-than-light particles. Experimental searches for tachyons have focused on detecting particles with negative mass-squared signatures in high-energy collisions, though no confirmed observations have emerged despite decades of investigation. Neutrino experiments have occasionally reported faster-than-light propagation, most notably the Opera Collaboration's 2011 measurement of superluminal neutrinos that was later attributed to experimental error. These null results strengthen the case against tachyonic particles, while highlighting the experimental challenges involved in testing relativistic predictions. The mystery of tachyonic quantum mechanics reveals how faster-than-light particles would experience inverted relationships between energy and velocity. making their quantum behavior profoundly different from ordinary matter. Tachyons would possess maximum velocity when their energy approaches zero and would slow down as their energy increases, creating quantum states that violate conventional energy-momentum relations. These exotic properties suggest that tachyonic quantum mechanics would require fundamental modifications to standard quantum field theory. The irony emerges in how particles designed to move faster than anything else would actually enable travel into the past rather than rapid movement through space. Tachyons transform speed into temporal displacement, making them time machines rather than conventional transportation devices. Perhaps most paradoxically, the fastest possible particles would arrive before they depart, making their journey times negative rather than minimal. Even more amusingly, tachyonic communication systems would receive messages before they are sent, transforming conversations into temporal paradoxes where effects precede their causes. Tachyonic dark matter represents a speculative possibility where faster-than-light particles could account for cosmological dark matter observations through their gravitational effects. These hypothetical tachyons would interact gravitationally with ordinary matter while remaining invisible to electromagnetic detection methods. However, their superluminal motion would create distinctive cosmological signatures that current observations do not support, making tachyonic dark matter scenarios highly constrained by existing data. The tachyonic anti-telephone paradox illustrates how faster-than-light communication could enable causal loops that violate free will and logical consistency. In this thought experiment, an observer uses tachyonic signals to send information to their own past, potentially creating situations where the observer receives information that contradicts their decision to send the original message. These paradoxes suggest fundamental incompatibilities between faster-than-light communication and the logical structure of spacetime. Lorentz invariance violations in some quantum gravity theories permit effective superluminal propagation without requiring explicit tachyonic particles. These theories modify the dispersion relations for ordinary particles at extremely high energies, potentially allowing faster-than-light propagation without the causality violations associated with conventional tachyons. However, such modifications must be carefully constrained to avoid observable violations of special relativity at currently accessible energy scales. Modern approaches to tachyon physics focus on understanding their role as indicators of theoretical instabilities rather than as physically observable particles. In this view, tachyonic modes signal the need for theoretical modifications that restore stability and causality rather than predicting new types of matter. String theory exemplifies this approach by treating tachyonic instabilities as guides toward more stable theoretical configurations rather than as fundamental features of the physical spectrum. The absence of observed tachyons provides strong evidence for the stability of our universe's vacuum state and the fundamental consistency of relativistic physics. If tachyons existed as stable particles, they would likely have been produced in high-energy cosmic ray interactions or particle accelerator experiments. Yet no convincing evidence has emerged despite extensive searches. This null result supports theoretical arguments that tachyonic instabilities typically resolve through phase transitions that eliminate faster-than-light modes. Tachyonic physics continues influencing theoretical developments in quantum field theory, cosmology, and string theory as a tool for understanding instabilities and phase transitions. While tachyons may never exist as observable particles, their mathematical properties provide valuable insights into the structure of field theories and the mechanisms that ensure causal consistency in relativistic physics. Their study reveals deep connections between causality, stability, and the fundamental architecture of physical law. Multiple timeline theories suggest reality branches to preserve logical consistency across temporal journeys, creating parallel histories where every possible resolution to temporal paradoxes coexists simultaneously. These branching universe models transform the grandfather paradox from a logical impossibility into a mere inconvenience. Travelers who prevent their own birth simply create new timelines where they were never born, while their original timeline continues undisturbed. Each temporal intervention spawns additional branches in an ever-expanding tree of alternative histories. The many-worlds interpretation of quantum mechanics provides a natural framework for understanding timeline branching through the continuous splitting of reality with every quantum measurement. In this view, all possible outcomes of quantum events occur simultaneously in parallel universes, creating a vast multiverse where every conceivable history unfolds somewhere within the infinite ensemble. Time travel would simply enable movement between these pre-existing branches, rather than creating new paradoxes or contradictions. Novikov's self-consistency principle offers an alternative resolution, where the universe permits only those time travel scenarios that remain logically consistent with established history. Under this principle, temporal travelers cannot alter the past because their interventions were always part of the historical record they attempt to change. The universe enforces consistency through physical mechanisms that prevent paradoxical actions, making time travel possible but constraining it within predetermined causal loops. The chronology protection conjecture, proposed by Stephen Hawking, suggests that physical laws themselves prevent the formation of closed time-like curves through quantum effects that destabilize time machines before they can operate. Virtual particles would create runaway feedback loops near temporal boundaries, generating infinite energy densities that destroy any mechanism capable of enabling time travel. This conjecture transforms time travel from a theoretical possibility into a physical impossibility protected by quantum mechanics. Dynamic timeline models describe temporal structures that respond actively to time travel interventions by adjusting themselves to maintain consistency. These self-healing timelines would automatically accommodate changes through ripple effects that propagate forward and backward through time, creating new causal patterns that preserve logical coherence while allowing genuine temporal modifications. The timeline becomes an active participant in temporal interactions rather than a passive substrate for events. The butterfly effect in chaotic systems suggests that time travel interventions, no matter how small, could cascade through sensitive dependence on initial conditions to create dramatically altered futures. A time traveler stepping on an insect in the past might trigger a chain of causally connected events that completely transform subsequent history through exponentially amplifying perturbations. This sensitivity makes precise control of time travel outcomes virtually impossible in complex dynamical systems. Quantum branching models propose that timeline splitting occurs automatically whenever time travelers make choices that could lead to paradoxes, with quantum mechanics determining the probability weights for different branches. Each possible action creates a quantum superposition of alternative timelines that collapse into definite histories only when observed or measured. This quantum approach to timeline dynamics combines multiple worlds physics with temporal mechanics in mathematically elegant ways. The block universe interpretation suggests that all moments in time exist simultaneously as points in four-dimensional spacetime, eliminating the need for timeline branching by treating time travel as movement through an unchanging geometric structure. In this view, temporal paradoxes become impossible because the past, present, and future coexist as parts of a single static reality, where changes cannot occur. Time travelers simply follow predetermined paths through the eternal spacetime manifold. Information-theoretic approaches to timeline consistency focus on the preservation of quantum information during temporal loops, suggesting that paradoxes resolve through mechanisms that prevent information loss or creation during time travel events. These models treat timeline branching as a form of quantum error correction that preserves the total information content of the universe while allowing temporal navigation. Information becomes the fundamental quantity that timeline dynamics must conserve. The mystery of timeline selection deepens when considering how branching mechanisms would determine which particular histories become realized among the infinite possibilities available at each temporal decision point. Some models propose anthropic selection criteria, where conscious observers preferentially inhabit timelines compatible with their existence, while others suggest that all branches possess equal reality regardless of observation. The selection problem connects time travel physics to fundamental questions about consciousness and reality. The irony manifests in how attempts to change the past through time travel might be precisely the mechanisms that create the past travelers seek to alter. Bootstrap paradoxes arise when information or objects appear to have no ultimate origin, existing in causal loops where effects become their own causes. Perhaps most paradoxically, time travelers might discover that their interventions were always necessary components of the historical events they intended to prevent. Even more mysteriously, the act of preventing a paradox might itself create the conditions that make the paradox possible, transforming causality into a self-referential system where logic becomes circular. Computational models of timeline branching reveal the mathematical complexity involved in tracking multiple histories through temporal interventions. These simulations suggest that even simple time travel scenarios could generate exponentially expanding numbers of alternative timelines, quickly exceeding any conceivable computational capacity for tracking their evolution. The computational requirements for understanding timeline dynamics might exceed the information processing capabilities of the universe itself. Empirical tests of timeline theories remain challenging because branching mechanisms operate at scales and in regimes currently inaccessible to experimental investigation. However, some proposals suggest that quantum experiments might reveal signatures of timeline branching through subtle correlations between measurement outcomes and hypothetical temporal interventions. These experiments would probe the foundations of quantum mechanics while testing the reality of alternative timelines. The ethical implications of timeline branching raise profound questions about moral responsibility across multiple histories. If every possible action creates alternative timelines where different choices were made, traditional notions of accountability become complex when consequences spread across parallel realities. Time travelers might bear responsibility for creating entire universes of suffering or joy through their temporal interventions, transforming ethics into a multidimensional problem spanning infinite histories. Modern interpretations of timeline physics incorporate insights from quantum gravity theories that suggest spacetime itself might possess discrete or emergent structure at microscopic scales. These approaches could naturally incorporate timeline branching through the fundamental quantization of temporal intervals, or through emergent spacetime dynamics that permit multiple causal structures. Loop quantum gravity and causal set theory both offer frameworks where timeline multiplicity might emerge from deeper geometric principles. The anthropic landscape of string theory provides another context for understanding timeline branching through the vast number of possible vacuum states available in higher dimensional physics. Each timeline branch might correspond to regions of spacetime with different effective physical laws determined by vacuum selection, creating not just alternative histories but alternative physics. Time travel could enable exploration of the string landscape through direct navigation between different vacuum configurations. Experimental approaches to timeline physics focus on detecting subtle quantum correlations that might reveal evidence of parallel realities or alternative histories. Quantum interference experiments, delayed choice measurements, and tests of Bell inequality violations all probe the foundations of quantum mechanics in ways that could illuminate the reality of multiple timelines. While these experiments cannot directly demonstrate time travel, they explore the quantum mechanical foundations that timeline theories depend upon for their logical consistency. Neutron stars and galactic centers create extreme temporal gradients throughout the observable universe, transforming spacetime into a complex landscape of flowing time where seconds stretch into hours and hours compress into moments. These natural laboratories demonstrate gravitational time dilation on scales that dwarf terrestrial effects, creating cosmic environments where time itself becomes as variable as temperature or pressure. The universe reveals itself as a temporal archipelago where each massive object creates its own unique chronological climate. Neutron stars, with masses exceeding our Sun compressed into spheres merely 20 kilometers across, generate gravitational fields so intense that time flows measurably slower on their surfaces compared to interstellar space. A clock positioned on a typical neutron star's surface would run approximately 30% slower than identical clocks in regions far from gravitational influence. This temporal compression means that neutron star inhabitants would experience roughly 7 hours for every 10 hours measured by distant observers. The surfaces of the most massive neutron stars approach the theoretical limit, where gravitational time dilation becomes so extreme that external observers would see surface processes nearly frozen in time. These objects exist just below the mass threshold for black hole formation, creating gravitational fields that stretch time to its breaking point without crossing the event horizon boundary. Material falling onto such objects would appear to slow dramatically as it approaches the surface, taking arbitrarily long to complete its final descent from the perspective of distant observers. Sagittarius AE, this supermassive black hole anchoring our galaxy's center, contains over 4 million solar masses within a region smaller than our solar system. Stars orbiting close to this cosmic giant experience extreme gravitational time dilation as they sweep through their elliptical paths, aging measurably slower during their closest approaches to the galactic center. The star S62, with its highly eccentric orbit, experiences time dilation factors of several percent during its periapsis passages. Millisecond pulsars, neutron stars rotating hundreds of times per second, create complex combinations of gravitational and kinematic time dilation that vary systematically across their surfaces. The equatorial regions of these rapidly spinning objects move at significant fractions of light speed, experiencing both the gravitational time dilation from the neutron star's mass and additional kinematic effects from their high velocities. This creates temporal gradients across the stellar surface, where different latitudes experience different rates of time flow. White dwarf stars, though less extreme than neutron stars, still generate significant gravitational time dilation due to their dense configurations of electron-degenerate matter. These stellar remnants typically contain roughly half a solar mass compressed to Earth-like dimensions, creating surface gravity thousands of times stronger than Earth's. Time flows approximately 99.9% as fast on white dwarf surfaces compared to interstellar space, creating measurable but modest temporal effects for hypothetical surface observers. galaxy clusters, the largest gravitationally bound structures in the universe, create weak but extensive gravitational time dilation fields that influence temporal flow across millions of light years. These massive assemblages of dark matter, galaxies, and hot gas create gentle temporal gradients that become significant only when accumulated over cosmic distances and timescales. Observers within rich galaxy clusters would age slightly slower than those in cosmic voids, though the effect remains imperceptible over human lifetimes. The cosmic web's large-scale structure creates a complex temporal topography throughout the observable universe, with time flowing fastest in cosmic voids and slowest within massive filaments and nodes. This temporal landscape evolves over cosmic time as structure formation proceeds, creating a dynamic pattern of time dilation that influences the evolution of galaxies, stars, and planetary systems. The universe ages at different rates in different locations, making cosmic time fundamentally dependent on position within the large-scale structure. Gravitational lensing observations reveal how massive objects between distant sources and Earth create multiple images with different light travel times, effectively enabling observation of the same astronomical events from multiple temporal perspectives. Strong lensing systems can create time delays of days to years between different images of variable sources like quasars or supernovae, providing natural experiments in gravitational time dilation. These systems demonstrate how massive objects create not just spatial distortions, but temporal multiplexing of distant events. The mystery of temporal synchronization across the universe deepens when considering how different gravitational environments would measure cosmological time differently. The cosmic microwave background provides a natural reference frame for cosmic time, yet observers in different gravitational potentials would measure different ages for the universe due to their local time dilation effects. This gravitational redshift of cosmic time creates subtle variations in measured cosmological parameters that depend on the observer's location within the universe's gravitational field structure. The irony emerges in how the universe's most extreme objects become natural time machines that enable passive time travel simply through proximity to their gravitational fields. Astronauts orbiting close to neutron stars or galactic centers would automatically travel into the future relative to distant observers, requiring no exotic physics or impossible technologies beyond the ability to reach these extreme environments. Perhaps most elegantly, the universe provides free time travel to anyone brave enough to approach its most dangerous objects. Even more paradoxically, the same gravitational fields that could crush matter into exotic states also provide the gentlest possible acceleration into the future through pure geometric effects on temporal flow. Binary neutron star systems create time-dependent gravitational fields that vary as the stars orbit each other, producing oscillating time dilation effects that change systematically with orbital phase. Observers near such systems would experience temporal flow that speeds up and slows down in rhythm with the binary orbit, creating a gravitational metronome that marks time through geometric effects. These systems lose energy through gravitational wave emission, causing their orbits to decay and their temporal oscillations to accelerate until merger, tidal disruption events, where stars pass too close to supermassive black holes and become gravitationally shredded, create spectacular demonstrations of extreme time dilation as stellar material falls toward the event horizon. Different parts of the disrupted star experience different gravitational potentials and thus different rates of time flow, creating temporal stretching effects that complement the spatial tidal forces. These events provide observational laboratories for studying time dilation in dynamic, extreme gravitational environments. Accretion disks around compact objects create radial gradients in gravitational time dilation that influence the physics of matter spiraling towards central masses. Material in the inner regions of these disks experiences severe time dilation compared to outer regions, affecting the rates of atomic processes, magnetic field evolution, and radiative cooling. These temporal gradients contribute to the complex dynamics of accretion flows and the generation of jets and outflows from compact objects. Future space missions to neutron stars or black hole environments would enable direct experimental tests of extreme gravitational time dilation using atomic clocks and precision timing systems. These missions would provide unprecedented opportunities to study general relativity in the strong field regime while exploring the practical implications of natural time dilation for space exploration and communication. The technological challenges of operating in such extreme environments would be offset by unique scientific opportunities to probe spacetime's fundamental structure. Cosmological models incorporating inhomogeneous matter distributions reveal how the universe's temporal structure has evolved from the relatively uniform conditions following the Big Bang to the complex temporal landscape created by billions of years of structure formation. This temporal evolution of time itself represents one of cosmology's most subtle effects, where the universe's expansion history becomes entangled with the gravitational time dilation produced by evolving cosmic structure. The detection of gravitational waves from merging compact objects provides new tools for studying extreme time dilation effects through the precise timing of gravitational wave signals. These observations probe the strong field regime of general relativity, while revealing how extreme gravitational environments influence the propagation of spacetime disturbances themselves. Gravitational wave astronomy opens new windows for exploring the universe's temporal complexity through direct detection of spacetime dynamics. Dark energy stretches space itself, carrying galaxies away faster than light can follow, creating a cosmic expansion that generates its own form of time travel through the fundamental growth of space-time fabric. This mysterious force, comprising roughly 70% of the universe's total energy density, drives an acceleration that began dominating cosmic evolution approximately 5 billion years ago. The expansion creates horizons beyond which galaxies recede at superluminal velocities, not through motion within space, but through the creation of new space between distant objects. The Hubble constant measures the current rate of cosmic expansion at approximately 70 kilometers per second per megaparsec, meaning that galaxies separated by 1 megaparsec move apart at 70 kilometers per second due to expansion alone. This expansion rate creates observable time dilation effects as light from distant galaxies becomes red-shifted by the stretching of space during its journey to Earth. The cosmological redshift provides a direct measure of how much the universe has expanded since ancient light began its journey toward terrestrial observers. Type Ia supernovae observations in the 1990s revealed that cosmic expansion is accelerating rather than decelerating, indicating the presence of dark energy with negative pressure that drives space apart against gravitational attraction. These stellar explosions serve as standard candles whose apparent brightness reveals their distance, while their redshift indicates recession velocity. The combination demonstrates that distant supernovae appear dimmer than expected for a decelerating universe, providing evidence for accelerated expansion. The cosmological constant. Einstein's original proposal for explaining cosmic acceleration represents the simplest model for dark energy as a constant energy density inherent to empty space itself. This vacuum energy would maintain constant density even as space expands, creating pressure that drives continued acceleration. However, naive calculations of vacuum energy density from quantum field theory exceed observed values by factors of 10 to 1, creating the worst theoretical prediction in physics history. Quintessence models propose that dark energy arises from a slowly evolving scalar field that changes its energy density over cosmic time, potentially explaining why dark energy dominance began relatively recently in cosmic history. These dynamic dark energy models predict subtle variations in expansion rate that might be detectable through precision cosmological observations. The field's evolution could theoretically reverse, leading to future cosmic contraction rather than eternal expansion. The cosmic event horizon represents a fundamental boundary beyond which galaxies become causally disconnected from our observable universe due to accelerated expansion. Objects beyond this horizon appear frozen in time from our perspective, as their light becomes increasingly redshifted and delayed by the expansion of intervening space. This horizon shrinks over time in an accelerating universe, eventually limiting our observable cosmos to an ever smaller fraction of the total universe. Phantom dark energy models predict even more extreme acceleration, where the expansion rate itself accelerates, leading to a big rip scenario where space expansion eventually overcomes all fundamental forces. In these models, dark energy density increases over time rather than remaining constant, ultimately tearing apart galaxies, stars, planets, and eventually atoms themselves through runaway spacetime expansion. The universe would end in finite time through the complete dissolution of all bound structures. The multiverse implications of cosmic acceleration suggest that our observable universe represents merely one bubble within an eternally inflating multiverse where different regions experience different expansion histories and physical laws. Eternal inflation driven by dark energy analogues could create an infinite ensemble of causally disconnected universe regions, each with potentially different values of fundamental constants. Our accelerating universe might be just one member of this vast cosmic ensemble. Vacuum decay scenarios propose that our current vacuum state might be metastable, potentially decaying to lower energy configurations that would fundamentally alter physics throughout space. Such transitions would propagate outward at light speed, creating expanding bubbles of new physics that would completely transform the nature of matter, energy, and space-time itself. The discovery of cosmic acceleration raises questions about vacuum stability and the ultimate fate of physical law. The coincidence problem asks why dark energy density and matter density are comparable today when they evolve differently over cosmic time, suggesting that we live during a special epoch in cosmic history. This temporal coincidence might indicate anthropic selection effects, where conscious observers can only exist during brief periods when cosmic acceleration permits stable structure formation. Alternatively, it might signal connections between dark energy and matter that remain poorly understood. The mystery of dark energy's physical origin remains one of cosmology's deepest puzzles, as no known fundamental physics naturally produces the required energy scale and equation of state. The energy scale associated with dark energy corresponds to physics at 10 or 3 electron volts, far below any known fundamental scale in particle physics or gravity. This enormous hierarchy problem suggests that dark energy might arise from physics beyond the standard model of particle physics and general relativity. The irony manifests in how the universe's acceleration creates a natural time machine that carries us into a future where most galaxies have disappeared beyond the cosmic horizon, leaving future observers in an apparently empty cosmos. The same expansion that enables us to observe the universe's ancient history through distant galaxies will eventually hide that history from future civilizations. Perhaps most paradoxically, the universe grows larger by creating more space, not by expanding into pre-existing space, making cosmic expansion fundamentally different from ordinary motion. Even more mysteriously, empty space itself possesses energy that drives its own multiplication, suggesting that nothingness might be the universe's most dynamic component. Baryon acoustic oscillations, sound waves that propagated through the early universe before matter and radiation decoupled, provide a standard ruler for measuring cosmic expansion history through their imprints on galaxy clustering. These oscillations created characteristic scales in the matter distribution that serve as cosmic chronometers, revealing how expansion rate has changed over billions of years. The measurements confirm accelerated expansion while constraining models of dark energy evolution. The integrated Sachs-Wolf effect describes how cosmic acceleration influences the cosmic microwave background radiation through the time-dependent gravitational potentials created by evolving large-scale structure. Photons climbing out of gravitational wells experience net energy loss when those wells decay during cosmic acceleration, creating subtle temperature patterns in the microwave background. These observations provide independent confirmation of dark energy through its influence on ancient light. Future observations with next-generation telescopes and surveys will probe dark energy through weak gravitational lensing, galaxy clustering, and supernova observations that map cosmic expansion to unprecedented precision. These measurements will test whether dark energy remains constant or evolves over time, potentially revealing its fundamental nature through detailed observations of cosmic acceleration history. The results could distinguish between cosmological constant models, quintessence, and modified gravity alternatives. Laboratory searches for dark energy focus on detecting possible violations of the equivalence principle or modifications to gravitational physics that might arise from scalar field dark energy. These experiments probe fundamental physics through precision tests of gravity, while searching for connections between cosmic acceleration and laboratory-scale phenomena. While dark energy effects remain negligible at laboratory scales, precision measurements might reveal subtle signatures of the physics driving cosmic acceleration. The anthropic implications of cosmic acceleration raise profound questions about whether conscious observers could exist in universes with different dark energy densities or expansion histories. Too much dark energy would prevent structure formation, while too little might lead to rapid cosmic collapse before biological evolution could occur. These considerations connect cosmology to fundamental questions about the nature of physical law and the possibility of multiple universes with different properties. Theoretical models attempting to explain dark energy range from modifications to general relativity on cosmic scales to extra-dimensional physics, where gravity leaks into higher dimensions. These approaches seek to avoid the enormous fine-tuning required for cosmological constant models, while providing natural explanations for why cosmic acceleration began recently. The theoretical landscape remains rich with possibilities that future observations might distinguish or eliminate. The universe's first light still travels toward us, carrying information from time's beginning across billions of years of cosmic expansion, creating a natural time machine that preserves the ancient cosmos in frozen electromagnetic waves. This cosmic microwave background radiation, released 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, provides a direct snapshot of primordial conditions that shaped all subsequent cosmic evolution. Every direction we observe reveals the same ancient epoch, making the entire sky a temporal window into the universe's infancy. The surface of last scattering marks the moment when photons decoupled from matter as the universe expanded and cooled below the ionization threshold of hydrogen atoms. Before this epoch, the cosmos remained opaque to electromagnetic radiation, as photons scattered continuously off free electrons in the primordial plasma. The decoupling created a sphere of transparency that expanded outward at light speed, allowing radiation to propagate freely through space for the first time in cosmic history. Temperature fluctuations in the cosmic microwave background, measured with extraordinary precision by satellites like WMAP and Planck, reveal the tiny density variations that served as seeds for all cosmic structure formation. These fluctuations, typically varying by mere millionths of a Kelvin, encode information about the universe's geometry, composition, and physical conditions during its earliest moments. The statistical properties of these temperature patterns provide our most direct evidence for cosmic inflation and the quantum origin of cosmic structure. Baryon acoustic oscillations imprinted in the microwave background radiation preserve acoustic waves that propagated through the early universe before matter and radiation decoupled. These sound waves travelled at 1/3 the speed of light through the coupled photon-baryon fluid, creating characteristic angular scales in the temperature fluctuations that serve as standard rulers for measuring cosmic geometry. The acoustic features confirm the flat spatial geometry of the universe while constraining the densities of dark matter, dark energy, and ordinary matter. Polarization patterns in the cosmic microwave background carry additional information about the early universe's physical conditions, particularly the ionization epoch when the first stars and galaxies began ionizing surrounding hydrogen gas. The polarization arises from Thomson's scattering of radiation off electrons, creating distinctive patterns that encode information about the universe's thermal and ionization history. Future measurements of B-mode polarization could reveal gravitational waves from cosmic inflation, providing direct evidence for quantum fluctuations in spacetime itself. The cosmic neutrino background, predicted to exist alongside the microwave background, consists of relic neutrinos that decoupled from matter approximately 1 second after the Big Bang. These primordial neutrinos, cooled by cosmic expansion to temperatures of roughly 2 Kelvin, carry information about the universe's earliest moments, when fundamental forces operated under conditions impossible to recreate in terrestrial laboratories. Direct detection of this neutrino background remains beyond current experimental capabilities, but could provide unprecedented insights into primordial physics. Gravitational waves from cosmic inflation, if they exist at detectable levels, would create distinctive signatures in the cosmic microwave background polarization through their interaction with matter during the surface of last scattering. These primordial gravitational waves would provide direct evidence for the rapid exponential expansion that occurred during the universe's first fraction of a second. The amplitude of these signatures would reveal the energy scale of inflation and potentially discriminate between different models of the inflationary epoch. The cosmic infrared background preserves light from the first stars and galaxies, redshifted by cosmic expansion into infrared wavelengths that encode information about the earliest epochs of structure formation. This radiation carries signatures of the first stellar populations, their formation rates, and the reionization process that transformed the universe from neutral to ionized. Measurements of infrared background fluctuations reveal how cosmic structure evolved during the universe's adolescence, bridging the gap between the cosmic microwave background and locally observable galaxies. Cosmic archaeology through ancient light reveals how fundamental constants and physical laws have remained stable over cosmic time, as spectroscopic observations of distant galaxies probe atomic physics under conditions billions of years in the past. The wavelengths of spectral lines from distant objects provide precision tests of whether quantities like the fine structure constant have evolved over cosmic history. These observations suggest remarkable stability in fundamental physics across vast scales of space and time. The mystery of the cosmic microwave background's extraordinary uniformity across the sky initially posed a horizon problem. How could causally disconnected regions of the early universe achieve such similar temperatures? Cosmic inflation provides the leading solution by proposing that our observable universe evolved from a tiny, causally connected region that underwent exponential expansion. This inflationary paradigm transforms an apparent problem into evidence for exotic physics during the universe's earliest moments. The irony emerges in how looking outward through space automatically becomes looking backward through time, making astronomy inherently historical as we observe increasingly ancient epochs at greater distances. The most distant galaxies appear as they existed when the universe was less than 1 billion years old, while the cosmic microwave background shows us conditions when the cosmos was merely 380,000 years old. Perhaps most remarkably, we can observe the consequences of quantum fluctuations from the universe's first 10⁻⁵ seconds, preserved in temperature patterns across the entire sky. Even more mysteriously, the ancient light surrounding us carries more information about cosmic origins than any amount of theoretical speculation, making direct observation of the past our most powerful tool for understanding fundamental physics. Future cosmic microwave background missions will probe ever subtler signatures of primordial physics, potentially detecting gravitational waves from cosmic inflation, measuring the sum of neutrino masses through their influence on structure formation, and constraining exotic physics scenarios like cosmic strings or topological defects. These observations will push our understanding of the early universe to unprecedented precision, while testing fundamental theories of quantum gravity and particle physics. The cosmic web's large-scale structure preserves information about primordial conditions through the gravitational evolution of density fluctuations first imprinted during cosmic inflation. Galaxy surveys that map millions of objects across billions of light-years reveal how these ancient seeds grew through gravitational instability into the cosmic architecture we observe today. The statistical properties of galaxy clustering encode information about dark matter, dark energy, and the physics of structure formation. Cosmic variance limits our ability to extract information from the cosmic microwave background because we observe only one realization of the primordial fluctuation field from our particular location within the universe. This fundamental limit means that some cosmological parameters cannot be determined to arbitrary precision regardless of measurement accuracy. The universe's finite size and our single vantage point impose ultimate constraints on how much we can learn about cosmic origins through electromagnetic observations. The anthropic implications of cosmic microwave background observations raise questions about whether the observed fluctuation amplitude represents a unique value required for structure formation, or merely one possibility among many in a multiverse ensemble. The amplitude must be large enough to enable galaxy formation, but small enough to avoid creating black hole dominance, suggesting possible anthropic selection effects. These considerations connect observational cosmology to fundamental questions about the nature of physical law and cosmic uniqueness. Quantum mechanics in the early universe connects microscopic uncertainty principles to macroscopic cosmic structure through the amplification of vacuum fluctuations during cosmic inflation. The temperature patterns we observe in the cosmic microwave background may represent the fossilized remains of quantum uncertainty from the universe's earliest moments, scaled up to cosmic proportions through exponential expansion. This connection between quantum mechanics and cosmology provides our most direct observational link to quantum gravity physics. The eternal preservation of ancient light in cosmic expansion creates a natural archive where information from every epoch of cosmic history continues propagating through space, waiting to be observed by appropriately positioned detectors. This cosmic library contains the complete electromagnetic history of the universe. Though accessing different chapters requires traveling to different locations or waiting for light from various epochs to reach our position, the universe serves as its own memory system, storing information about its past in patterns of radiation that continue propagating through expanding space. The cosmic background radiation continues its ancient journey, carrying whispers from when time itself first learned to flow freely through space. These photons, older than any star, older than any galaxy, drift through the expanding darkness with infinite patience, their message unchanged across 13 billion years of travel. They speak of a universe once hot and dense, now cool and vast, yet somehow still connected to its earliest moments through the persistent memory of light. Spacetime curves gently around every mote of matter, creating subtle valleys and hills in the four-dimensional landscape through which all existence unfolds. Each atom, each grain of dust, each distant quasar contributes its small signature to the cosmic geometry, weaving space and time together into patterns of such delicate complexity that consciousness itself might emerge from their intersection. The universe breathes through expansion and contraction, through the slow dance of matter and energy across scales both infinitesimal and infinite. Time flows differently everywhere, fast on mountaintops, slower in valleys, crawling near massive objects, racing through cosmic voids. Yet somehow, through all these variations in temporal rhythm, causality persists, information propagates, and the arrow of time maintains its steady direction toward greater entropy and complexity. The universe ages at different rates in different places, creating a temporal landscape as rich and varied as any geography of space. Perhaps time travel exists all around us in forms so gentle we barely notice in the differential aging of atomic clocks, in the redshift of ancient starlight, in the frame dragging of rotating planets. Perhaps the universe has always been a time machine, carrying us forward through expanding space toward a future we help create through our very observation of cosmic history. The cosmos tells its story through light that has travelled since time began, making every moment an encounter with eternity. The mathematics that describe curved space-time, quantum entanglement, and cosmic expansion suggest possibilities that transcend our everyday experience of temporal flow. Whether through wormholes or cosmic strings, through closed time-like curves or quantum loops, the universe seems to whisper that time itself might be more flexible, more forgiving, more mysterious than our intuitions suggest. In the end, we find ourselves suspended between certainty and wonder, between the known laws of physics and the vast unknowns that surround us on every scale. The ancient light fades into silence, carrying its secrets onward through the expanding dark, while new photons begin their own billion-year journeys toward distant observers who may someday decode their temporal messages with instruments we cannot yet imagine.